welcome back to my limit series. Today, we are going to prove a property about limits. Specifically, the fact that the limit as x approaches x naught of a constant times a function is equal to that constant times the limit as x approaches x naught of the function. Now, in your calculus classes or whatever class where you were computing limits, this might seem to be an obvious thing that you can do, but proving this is another task altogether. Now, before we go on to the formal proof, there are two things I want to go over. The first is the trivial case, that being where our constant c is equal to 0. Now, if we think about it, for the first part, if c is equal to 0, then our 0 times f of x is equal to 0. And the limit as x approaches x naught of 0 is 0. Now, looking on the right side, we have c, in this case is 0, so 0 times something, 0 times anything is 0. So therefore we have 0 is equal to 0. And that's kind of a trivial case. Now the second thing is that in order to prove this, we actually have to make an assumption about our limit. So we can say something like, there exists an L in the real numbers such that the limit as x approaches x naught of f of x is equal to L. This is just saying that this limit right here exists. And we will show that if this limit right here exists, then this equality holds true. In order to prove the statement that was on the board earlier, we need to use the definition of a limit. So let's look at what we are assuming and go from there. So we are assuming that the limit exists, right, for some L, which means for all epsilon greater than 0, there exists a delta, which we'll call delta A for assume, such that for all x, right, whenever x is within delta of x naught, the thing it's approaching, which is the same thing as saying that whenever 0 is less than this absolute value of x minus x naught, which is less than delta, that this implies the following, the fact that our f of x minus our L is less than epsilon. This is what we are assuming using our quantifiers, using the definition of a limit. And what we want to prove is the following, right? Is the fact that the limit as x approaches x naught of c times our f of x is equal to what, right? Right, if we're trying to prove that we can pull this constant out, then that would be our constant times the limit is equal to L. So therefore, it would be our constant times the limit, c times L. And so we can show what this implies. Again, for all epsilon greater than 0, epsilon is an arbitrary distance. There exists a delta, we can find a delta, but we haven't found it yet, and we need to find it to prove this, such that for all x, whenever 0 is less than x minus x naught is less than the delta, that this implies the following, that what's inside the limit, c times f of x minus c times L, that this is less than epsilon. So this all looks good. There's one more thing that I want to add. And that is, instead of saying that f of x minus L, the distance between those two is less than epsilon, I'm going to add that it's actually less than epsilon minus the absolute value of c. Now, if you saw my previous video and you're saying, well, doesn't this contradict the definition of a limit that I said before? Well, we have to think about what does epsilon represent. And the idea is epsilon isn't just one number, but it's any positive real number. Which means what we're saying is that f of x minus L should be less than any positive real number. So epsilon represents any positive real number, and epsilon divided by another positive real number, right? Because our C is in the real numbers. That our epsilon divided by absolute value of C by a positive real number is still a real number because the real numbers are closed under division. So therefore, even though this is like technically a different value, this is communicating the same idea. That f of x minus L, right, that absolute value of that difference is less than any real number. And therefore, we can use this to prove the fact that we want to prove. So now, let's prove what I have written in red. So, our epsilon, right, is arbitrary, but our delta is something that we have to find. We have to show always exists. So, let's say this delta is equal to this delta up here, right? That would be convenient if that worked. So, let's just suppose delta is equal to delta A, right? Therefore, right, whenever x is within delta of x naught, we know that this inequality is true. And we're trying to show that with the same condition for x, that this bottom inequality is true. So we can safely assume, right, that the distance between f of x and L is less than epsilon divided by C, by absolute value of C. So first we can multiply this C over to the other side, which gives us absolute value of C times absolute value of f of x minus L is less than epsilon. Now what can we do from here? Well, in my video about absolute values, we actually know that if we have the absolute value of something times the absolute value of something else, we can actually take the absolute value of that whole product and we find that it's the same thing. So now we have the absolute value of C times f of x minus L, right? Which is the same thing as we had before. So it's still less than epsilon. And then we can distribute this C here. So then we get C times f of x minus L times our C is less than epsilon. And therefore, we have a proof that the limit of a constant times a function is the same thing as the constant times the limit of the function. Thank you very much for watching.